Hello, I'm John Rose, JVM architect, and this is my favorite professional time of the year to be together with you folks and exchanging notes and figuring out where the JVM and the languages on top of it are going. And I think all the interesting stuff is being said by other folks about Project Valhalla, Project Panama. I'm going to fill in a bunch of stuff that maybe is worth talking about also, and I'll make some generalizations about where I think the JVM is going and how we think we might get there. But I just want to acknowledge the great speakers so far, and I'm looking forward to the ones that are coming, because that's the real meat of this conference. But I hope I will give you some inspiration and maybe some crazy ideas along with me. I have 45 slides in 45 minutes, and the slides are not your Mark Reinhold Zen slides where there's just a picture. I wish I could do that, but what I like to do is pack my slides until I'm full and my ideas are spilling out in my brains, and then I say, well, of course I won't get to all of this, but at least I'll post my slides, and then we'll have a capture of what the world looked like at that point. So here we go again. You've seen it before, I think. I want to say that this is a special kind of crystal ball that works only for geeks and not for marketers or lawyers. But that's okay, we're all down with that. Last year I gave a talk on where we think the VM will be after 20 years and another 20 years. So now we're at 19 and counting. And I want to replay those goals basically verbatim so we can compare with what we're doing right now at the moment. There should be a uniform model. In other words, our models should be getting more and more uniform, not more and more discrete and with more sidecars and add-ons. We want primitives and objects and arrays and values to look more and more similar to each other so we can use the same high leverage plays for all of them at the same time. We want efficient data layouts. We want efficient code. We want it to be both shared and customized, if we can pull that off. That's kind of difficult, but you know it's possible if you pay attention. We want something that is post what I call dinosaur threads. I'll talk more about that later, but we want very good right-sized granular concurrency, which generally means one or two variables, and var handles are a great move in that direction since last year and the year before. We want our JVM to be interoperable with a wide variety of other system components, including languages that are running beside the JVM and not just on top of it. We want it to be useful for those languages that run on top. We want lots of really cool languages like Scala and Clojure and so forth to run on top of the JVM. Excuse me. And rather uniquely for Java, we want it to run 30-year-old, or at that point 40-year-old dusty decks. How many of you know what a dusty deck is? Okay. It actually refers to the ancient practice of encoding software in cards of paper and where you punch holes in them. And then a deck of these cards has your program on it, and it becomes dusty after a while, and you still want to run it through the card reader. Well, we have a jar reader, and we want to be able to read virtually dusty jars. And of course, it has to be performant. And the fun thing, one of the things that really makes the job of JVM engineer interesting is the hardware is always changing underneath you. Our JVM is more slowly changing than the hardware over which it runs, which means that we are always getting the latest chips and trying to figure out how to do the trick again on the new chip. It's really a blast, actually. All right, here's my one diagram. Here's a methodology for trend capture. I'm in the wrong room to say stuff like that, but it really amounts to looking at the trajectory of where you came from since 1.0 and what your current slope of your curve is in a very highly multidimensional space, and trying to guess where that's going next. And of course, the dotted line shows that you have no hope of guessing exactly right, but I'm still going to guess, and we're going to think about it together. So here are some trends. The JVM, I predict, will continue to emphasize predictability, which includes reliability and security. We don't want to give our users surprises. We want to be the JVM people run on when they want to know that their jobs are going to get delivered. We want deterministic GCs, as Bernard hinted at. We want manageability, which means ever more ways of looking under the hood and seeing what's going on with your software system, especially as it becomes more and more magic. Sorry. We want the ability to monitor and manage the intricacies of how the system is working, especially when it's compiling and recompiling, and we have various pieces there. We want to do more. Another independent trend is scaling and density. We want those terabyte heaps. We also want to be able to do tiny microservices, maybe running a few of them in a JVM or maybe 1 million of them in a JVM, but independently. We want to be able to scale using sharing tricks. We want to start up fast. This is where we're going. This is what we're working on. I'm predicting that immutability will become more and more important, and for reasons that we've already heard today. I totally agree with those. We want a VM that will continue to be polyglot, that will interoperate with unmanaged languages, implement well-managed languages. Maybe in the next decade or so, we'll see C programs or C++ programs running in managed mode on top of the JVM. I wouldn't be surprised. Here's another one that's less obvious. I predict, and I think what we're aiming towards, is more layered implementations where instead of have a big wad of C++ and then a bytecode interpreter on top, you have various factored layers. There's maybe low layers of C++, mid layers of low-level Java, specially compiled AOT Java, Java components. This is what I would call Java on Java, which is, I think, a very important area of inflection to move the technology forward on. And Graal is one of the leading indicators of this. In general, we want strong layered abstractions where you can really reason about each abstraction without peeking underneath the hood, and yet have the system drill through them in order to optimize. It's what everybody wants. One of the evidences of this that's already exists is the INDI macro instruction, which is it's a way of layering sort of in a fat area of the bytecode. It's a bytecode instruction, but it's a bytecode instruction that, like a macro, expands to many more bytecode instructions. So it provides not just a narrow line between C++ and bytecode, but a way for bytecode to edit itself. And we want to see more of that stuff moving on. These are my predictions. Now, let me give you some big ideas that implement these predictions and in a promising way. Interoperability. Let's make native code and data look more like managed code and data. This is what one of many unifying or heal the rift or caulking over the cracks, I think is how Brian said it, where we take things that didn't look like each other before, so they had to be managed with separate tactics, and we make them be more like each other. Okay, sorry. How do we heal the rift between managed and unmanaged data? There's going to be a lot of talks on Wednesday about this for Project Panama. We think we have some good ideas. It's basically up-leveling and adding layering. There's that theme. Adding layering to unsafe so that there are safe ways to use pointers which can point both on and off heap, which is a designed-in characteristic of unsafe from the beginning. This interoperability depends, there's always dependencies between these big ideas. It depends partly on value types. You want value types to represent platform types that aren't in the Java's repertoire of primitives. You want to use it to, you want parametric polymorphism to deal with things like foreign arrays. You also need some sort of bridging technology to bridge through special ABIs to non-Java methods. This kind of interoperability, when it wins, gives you a tighter coupling and a more virtuous cycle with a wider range of data types, not just the ones defined on the Java heap, but off heap, numeric types, various kinds of bulk data. It gives you better access to C APIs that haven't been retranslated into Java yet and maybe never will be. You want to be able to sometimes call libc type functions. You want to, interestingly, and this goes with the trend towards more and more exotic kinds of hardware, you want to get to the latest instructions from your ISA. We think one of the new ways to get to things like AVX or AVX 512 is to make them intrinsics at the Java level and have them punch all the way through using snippets, and Vladimir will talk about that later. In the interests of speed, I'm just going to continue, but I want to give you a good picture. This is coming to a towel near you. The theme of platform interoperability shows up partly in the hammer of density and the shield of flat data. One of the reasons we want to go off heap is so we can control the storage layouts more tightly. Okay, here's another big idea. Java on Java. What do I mean by that? I mean implementing the Java engine, the Java execution environment using Java. So Java is implemented on top of itself. So it's a meta-circular move. It heals the rift between having to code in C++ and Java at the same time. It lets you use one high leverage point, the Java compiler and the Java JIT and the Java type system, to manage more of the important parts of your system. It depends partly on native interconnection, which was talked about earlier, but which might be called Project Panama. And it also depends on being able to integrate Java components more tightly into Hotspot without having Hotspot go into infinite regress trying to manage itself. Depends partly on flat data. In particular, JITs have these tendency to make very huge spikes up to the gigabyte scale of temporary IR. And those huge spikes are limited in part by the density quality of the data structures that are in those spikes. So once again, flat data shows up as an important goal. In any case, Java on Java, which I hope in the OpenJDK community we can begin exploring together this year using Graal as a vehicle. It reduces all kinds of costs. And it lets us take more control over our own destiny. The current practice of Java on Java exists. This is a vector that has some basis in reality. The whole JDK is written in Java, after all. There are some languages where lots of the runtime is written in some other language. That's not the case for Java. Much of the libraries are written in Java. And the method handle runtime, for example, is written in this low-level sort of self-generating Java. And the AOT compiler is written in Java and can produce machine code. So, and then further experiments of Java on Java are Graal is the obvious one. Also something called Substrate VM, which we've heard about in previous years, which is sort of a way to shrink wrap applications down into smaller envelopes than Java applications. And something called, that was invented exactly 1 year ago in an after party for this conference, the Bifrost interpreter. The Bifrost bridge is the Rainbow Bridge to Valhalla. And we want to do some of our later prototyping using a metacircular bytecode interpreter, which Brian Getz put together, uncontrollably inspired after last year's meeting. By the way, coming to a towel near you, here's the Graal reference. That's what that thing is. You'll see it on your towel. It's right next to Valhalla. All right, what else? And post-threading, that's what I call it. Threads are dinosaurs. Threads have attracted features. So to the point where a thread is, the committee that designed threads, hardware, software, and Java, that committee would, the names would fill a phone book. It's just a huge number of different ideas all glommed together. There's no way you can take that and virtualize it and make it small again. So we need something smaller than threads. And we've been talking about this. Charlie ran a workshop years ago when we were gathering fiber requirements. We're still thinking about it. I want to present a few ideas. But basically, we need to not virtualize them and shrink them. We need to work around dinosaur threads. We need to leave the fossiliferous parts behind. So sort of the working title for that is Fibres. And it depends on some very tricky cuts in the JVM interpreter and JIT, but the metacircular interpreter is helping us do those experiments, those early experiments. And of course, lots of library work, which we had a great talk 2 years ago on this, which helped spur some of this work today. Okay, another big idea, value types, that's already been covered, but I gotta say a few things about it, right? So this is caulking the seam. It depends on, here's an important dependency, and here's a reason why you're seeing so much talk about parameterized types and any types and specialization when we thought we were talking about values. And the reason for that is there's a really strong dependency. If we want to do value types, we need to know how to parameterize over them. If we're going to parameterize over them, we actually need to do most of the work just to parameterize over primitives. So it turns out there's a very natural initial delivery point of doing parameterization before you do full values. If you can parameterize an array list of int, you are most of the way to parameterizing an array list of unsigned or complex or point or whatever. And it also, so that's why we talk so much about parametric polymorphism. It's not because we forgot we were doing values. But that depends in turn on template-like classes. And when I say template, I want you to think C++, but I don't want you to think of something that's statically expanded. We have to do things with the JVM's specially flexible mix of static and dynamic. So, okay, so that requires deep cuts, again, to the JVM code and data model. We need to be able to model these strange class files that expand to multiple species. This is a big ticket item. This is why it hasn't been done by somebody in their garage already 20 years ago. It's just hard to do, but we're pushing on it this time. We're going to get it done. What do value types enable? Huge changes throughout the stack. I almost think of this as the Francis Fukuyama end of history for Java. This is the last big thing that Java needs, in my opinion, is the unification of primitives and objects, but with everything looking like a class and adding in user-defined primitives. Yeah, I mean, type-based encapsulation is really cool, right? Private, being able to mark things private and have them be hidden and encapsulated and have people ignorant what's behind them, have interfaces where there's zero leakage about what's underneath. We should be able to do that with values too. That's going to make a huge, huge difference. There's Valhalla. At the top of the Rainbow Bridge. Okay, so let me say a little bit more about parametric polymorphism. By parametric, I merely mean to suggest that the parameter can vary more freely than ever before. The type parameter used to be bound under object, it has to be a reference, and now it can be any denotable type, which is wonderful, or maybe even non-denotable ones. Wouldn't that be interesting? So fundamentally, it lets you make generalizations. For any t, here's what you can do with those t's. Oh, and you can assume that the t is comparable. Oh, that means I can do sorted algorithms on them. That's very cool. I can do all sorts of things like that. It depends, as I said, on templates, something like C++ templates, and it's dependent upon by any number of different things. In other words, this is another reason parametric polymorphism breaks off as an early deliverable before the full world of values, is there's a lot of stuff you can do with it just by itself, such as new array types. You can't express new array types as interfaces until you have the right kind of polymorphism, or foreign pointers for that matter. It's hard, because primitives are totally different. In fact, they have different numbers of slots, as Brian pointed out. That's something we've got to fix along the way. That's pretty, if that's a small thing you need to fix before you can get to the big stuff, you know, we're talking about a multi-year project here. This has already been covered, so I'm just going to say that the interesting solutions to this involve moves like fixing the 1-2 slot thing. So making the data model more uniform as a preparatory move. Or, for example, figuring out a way to bind an interface to a primitive, and eventually to a value, so that you can not only parameterize over primitive types, but actually say things about what those primitives can do once you've parameterized over them. I don't even want to talk about equality today, but that's, suffice it to say, you could talk for a whole day on equality and still be scratching your head, and we've been there, haven't we? Yeah. All right, what does it do for you, parametric polymorphism? Well, once you have a way of talking about any type as a type variable, then more things have methods, more things have interfaces, more things can be, you can create generic algorithms on them. And maybe it's not so new for those of us who code with C++ templates, but it'll have its own flavor in the Java world because there'll be a lot more dynamicity with the Java. It turns out that we have to reinvent some of the different levels of equality that Common Lisp had from the 80s. There's the pointer equality, there's the structural equality, and then there's the algorithmic equality. Those are all three different things. Structural equality means that my little struct has the same bits as this same typed other struct. That's EQV. We have to have something like that, it turns out. We were like forced to invent it for Java. And then, of course, the big one is the templated classes. We need to be able to have these templated classes move their layouts as you put different types in for the type parameters. So this field might be 64 bits here or 128 bits here, or it might be 0 bits in an extreme case. The same class, different species. We think we have models to do this semi-dynamically, which is extremely exciting. And here's a dangerous opportunity that falls out. There's folklore that the Chinese characters for crisis is dangerous opportunity, and I was going to hit that hard, but it turns out that's false. But in any case, I'm going to say it anyway. It's probably a dangerous opportunity that if you're going to generalize over a type variable that, say, you can add the instances together to collect them into a sum or multiply them to collect them into a product, well, maybe you got something like operator overloading going on. What could that mean? Could it be possible in this framework to have pluses and minuses be bound through interfaces to big integer as well as integer and long? And the answer is probably yes. Do we want to go that far? I don't know. We're feeling our way in the dark. Eventually, we'll grab a razor blade and then back off, but we're trying for it. So we get template classes, and then a class is, as Brian put so well, a unit of source code, and it's also a unit of abstraction. But then when you fill in the type parameters, the holes in the class, then you get a species. So what are we talking about? We're talking about polymorphism of the constants in the constant pool. We're allowing a constant pool to contain holes, and then when you fill that hole, then you get a species, which is one of a controlled population of instances of that class. I don't mean instance in the object sense, I mean instance in the type sense. So we use species instead of instance when we talk about it. So, but what else might a hole be? I mean, that takes us to a template model in the VM, which may supply other interesting features that haven't been figured out at the language level yet. What if a constant pool hole is a hole for a string, or more interestingly, a method handle, or maybe just an integer? Maybe it's the dimension of a fused array inside the object, in which case you're starting to build tuples and algorithms, and you're doing some of the same tricks you do in C++ with function arguments to templates, or array dimension arguments to templates. How many of you have used those sorts of template hacks? Yeah, it's pretty powerful stuff, isn't it? Yeah, I think we can do that and better with this stuff. Constants might, and then this is me just stretching and being crazy, but what if a constant could be a tuple descriptor where the one constant describes n types, and then somehow you link that through to n fields of those successive types? You've just got one class that represents all tuples. We could pull that trick, I think. I mean, there's some possibilities here once you sort of double down on the concept of a constant pool with holes in it. yeah, maybe this is a way to combine with Paul Sandoz's trick that was already referred to of having many sort of duplicate field variables and then overlay a local array on that. That's a very powerful data structure which C programmers take for granted and we can't use yet because we don't have fused inline arrays yet. All right, so I've already used up almost all my time to talk about the big ideas. Let me throw some really smaller ones. And when I say smaller, maybe it's just because they're farther away on the horizon, so they look small. You know, Everest looks small from a certain perspective. But here we go. Stack introspection. We've got some interesting experiments going on that. Length polymorphism is an idea which I think is of interest. I'll explain that in a second. Bootstrap methods everywhere. That's a whole talk all by itself, but it's fun because there's a lot of places you can put bootstrap methods to sort of make programmable some of the built-in behaviors of the VM, especially linkage behaviors. And I want to talk a little bit about immutability, but it was well covered already, so I'm going to skip over that real fast. I want to say that the design of all these things, it looks like just grabbing one interesting idea after another, and it feels like that sometimes, but what's really going on, or has to go on, is something like assembling a Chinese puzzle, which looks like a piece of disordered, irregular pieces at first, and even while you're putting it together, it looks like, remember how the Death Star looked when it was half assembled? You don't really know what it's going to look like, and it looks kind of irregular. In the end, it should look simple, and people just say, oh, of course you should have done it that way. What took you so long? But in the process, you and I know you have to put each piece and try it up in 4 different places, and finally it clicks in somewhere, and then you put in the next piece. And sometimes you have to do 3 at once. You know, with these Chinese puzzles, you have to like hold 3 pieces together before you put the 4th one in. It's like that with language design and with VM design. The only reason VM design is slightly easier than language design is because there aren't as many people throwing their opinions at you. There's like 2 orders of magnitude fewer people who care about VMs than care about languages, probably 3 orders. So I like my job. You can have yours, Brian. All right, stack reification. Let's walk live stack frames. Let's stop parsing strings out of stack frame elements. Let's get live classes, assuming we have a certain permission to do so. Let's not stop with that. Let's grab the rest of what's in the stack frame. Let's see which method it is. Let's see what the BCI was. Let's start looking at the local variables. Once we can pull out the full state of a stack, we can then perhaps do tricks like point a metacircular interpreter at it and run it our way the rest of the computation. Let's edit the stack. Let's replace those ongoing computation with the computation running our way. There's lots of use cases for this. You could dismount a blocking call. This is your preview of Fibres, but dismount a blocking call from a thread, kick the thread over to the next fiber, and keep the fiber with the blocking call, and then later on come back to the fiber when the call is ready. Generator coroutines. You basically say, okay, this piece is the generator. I'm going to respin it as a heap-based data structure. It's going to push stuff. This is what .NET does really well with their async stuff. Replace a serial algorithm by a parallel one. What if you start running something serial and then you notice it's taking a while and you realize your data set is growing to large proportions? Let's just replace the computation by the fork join version. All right. So, interesting idea, right? Pardon me, fighting off a cold. Let's talk about length polymorphism. What does that mean? What I mean by that is a single class that has different instances of different lengths, okay? And what all that really means is fused arrays. Here's a poster child. The string object has a sub-object which is an array of bytes or an array of chars. And that by itself, just the extra indirection costs, if you count it all up, 16 to 24 bytes. That's a lot, actually. That means that the amount of storage space we save by moving from a char to a byte representation, which we do in JDK9, and it's really cool, we can save that much and more for strings less than 24 in length by removing that extra indirection, also by fusing the objects. But in order to do that, you need variable length strings. That's hard, but there's some pieces that we know we need to do. And there's a generalization of that too. You can do B trees instead of red-black trees if you have private arrays. But it requires a number of things. It requires that hidden array to be proxied so that you can actually run BA load instructions against it and have the VM not explode because there's not a real array there. So that's more like arrays 2.0, isn't it? It requires some GC cooperation to have the variable length objects. And this is the most interesting one of all. It requires a deep refactoring of our new invoke special dance, which is like a security problem, and it's the worst part of the verifier, and it's, let's get rid of it and use factory methods instead of new invoke init. If we have factory methods and the factory method is responsible for allocating the object, he can tell from the constructor arguments how big it's supposed to be, he can create the instance, and that's what it takes to get fused strings and the other kind of hybrid objects. And why not have more than one array per object? You can do it. We do it in Hotspot today in C++. All right. Whoa, what happened to my slide? That's really weird. Okay, I want to talk about Bootstrap methods everywhere. I want to double down on BSMs. I want to use them wherever the JVM already has some sort of a non-trivial hook for resolution. And here are some cases. I want to, when I do an LDC of a constant, I want a hook there. When I resolve a constant method ref in my constant pool, I want a hook there. When I do a check cast or a type query, maybe I want a hook there, although that's a more terrifying thing. So this leads me to, and this is where my slides are getting backwards, but this leads me to 3 items: constants, bridge-o-matic, duck typing. Ready for the fast presentation? First of all, what's in a constant? Well, primitives, strings, classes, API points, Indian method handles, for Valhalla, so the things that Brian was showing. But maybe also we want constants which are arrays. A constant array, that would be pretty good, right? It's probably time for a constant array in our system. Lists, sets, maps, of course. Value types, why can't you have a constant enum in your constant pool? Answer, well, no really good reason, just haven't gotten around to it. And various other types. What about a constant that's a DSL snippet, a snippet of intermediate code that a compiler has put in that it's not time to render to bytecode just yet, but you want to render it like 3 times or a bunch of times? Wow, we could really use that, couldn't we? How about semi-constants, which are templates in a different sense of the word template? Things that are factories of partially constant, partially non-constant structure. So like a string, which we have in JDK9, we have a templating mechanism for string concatenation. The last sub-bullet items there are shamelessly stolen from some of Brian's dreams about what constants might look like, and of course it won't look like that in the end because it never does, but in any case, maybe you could do some sort of constant list or constant string that has interpolation points in it. The important thing is constants have to be not externally mutable. You may not change them, otherwise they're not constants, and you probably made a mistake putting them in the constant pool. We don't stop you from doing that right now with anonymous classes, but it's, like I said earlier, it's a party foul. And we want them to be materialized lazily like string. So here's a future-proof design, in my opinion. There should only be a few new types, not one for each constant. Like, there shouldn't be a constant enum. No, thank you. That would be a code smell. It should be programmable using BSMs. It should allow various clever factory schemes and encoding schemes. It should allow, it should have a sort of a small fixed overhead. It should allow delivery of large amounts of constant payload without lots of wrapper around it. Should work clearly for the kind of use cases we're talking about. So, 3 new constant pool types. 1, constant dynamic. Don't you just love it? It just captures the static dynamic angst yin-yang of the JVM. So a constant dynamic would have 2 subparts, a type and a bootstrap specifier, which further consists of a bootstrap method and an optional vector of arguments, which are further constants, so these things can recurse. It's resolved by executing the bootstrap method, slightly different signature than the one you're used to today. It doesn't return a call site, it returns the constant. Right, so it's not a metafactory, it's a factory. No point of linguistics there. But basically the same rules as Indy for dealing with all the edge cases. Constant group is number 2. There's an arity limit of 254 or something like that for bootstrap methods, just because of the way methods are set up. So pass a list, my gosh. Oh wait, we don't have a list. Yes, now we do. Constant group is a very long list of, you got it, more constants. And if we're clever, we can nest them in such a way so there'll be an efficient envelope for AST-like structures. We have group of group of group, like a Lisp-S expression. And finally, for the bits, constant bytes, up to, say, 2 gigabytes. Does that sound like enough for everybody? And you can have more of them if you need to have larger payloads. But basically, this is where your primitive arrays get their bits from. What's the format? Well, it's up to the factory and the static compiler to agree. Maybe it's gzipped. Maybe it's just a data input. I don't know. All right, application to arrays should be obvious. I'm just going to skip over this slide because I'm out of time. The important thing here, though, is that if you're going to do constant arrays, unlike constant lists, you need a new way to make arrays frozen. So frozen arrays are a sort of a side dependency of this whole scheme. That's what makes it worthwhile. An alternative is to not expose arrays, but expose some other interface that's backed by a non-mutable thingy. All right, bridge Omatic. That's easier to describe than the constants. What do bridges do? Well, we know what bridges do, so I'm skipping this slide. Let's allow a method to have its own bootstrap method. It doesn't have bytecodes, it has a bootstrap method. What does a bootstrap method refer to? Well, maybe it has a static constant that has some DSL in it, or maybe it's just a pointer to another method saying, adapt me. Maybe there's hints on how to adapt it. Maybe as type is all you need. That's all it is. So the method is resolved on first execution. BSM executes, returns, in this case, a method handle. That's all you need. It could be a call site, I don't know. It returns a method handle, and that becomes the behavior of that method as linked. Here's a trivia question. What kind of method has no bytecodes but is executable? Yep. Well, maybe what we're looking for is act native plus act bridge. That wouldn't be the worst thing in the world. Okay, what would we use it for? Well, existing bridges. Bridging becomes a very open-ended concept. What can you bridge to? Well, you can bridge to the future. You can bridge to a native API. You can bridge to some Panama thing. You can bridge to a piece of DSL. Here's another idea. Maybe the bridge logic is triggered not just for one particular type and name and type descriptor, but the name and any type. Wouldn't that be cool? Now we're beginning to talk about duck typing. Maybe there's name polymorphism. Maybe there's a backup auto-bridger on a class that will take any unrecognized method, and now we're back to the original invoke dynamic. These are all variations on the theme of bridge Omatic. And finally, for duck typing, it's more bridge Omatic more of the time. Basically, you equip an interface with a BSM that says, if I'm calling through this interface, you don't require a pre-existing subtype, supertype relationship with the receiver. You just look at the receiver, and if it's a class you haven't looked at yet, you run a BSM, and you do the matchup. And if you can match point to point, then my interface will complete that call to that object. There's some serious questions of where you put that information, whether you use a proxy or whether you can somehow retroactively change the class, which makes some of us run screaming, including me on a lucid day. In any case, the BSM makes all the matching decisions. So at that point, you can have multiple grades and types and opinions about what duck typing really means. It's all up to the BSM. And so, okay. The downside of all of this is your compiler has to be smart with this. This is a problem. What we need is a way for the Bootstrap methods, which especially as we put them in more and more places, to run in a predictable manner. We want to be able to have JLink spring Bootstrap methods optionally, just as we want JLink to be able to run framework code injections optionally, so that we can seal down the module, get the code, and share it, and not have it de-optimized the first time you use it. So the downside of all this BSM stuff, which cleverly we've already introduced as technical debt, is that we have to figure out what these Bootstrap methods do statically. And in fact, that's how some of the Java platforms already implement JDK8 Indy-based lambdas. They simulate the Lambda metafactory in the compile time, but just by special pleading. We need to do better than that, but we have to start with special pleading. All right. So, immutability. Like I said, I get to skip over this because it was already really treated really well. You can read the slides. I think that it would have been cool if Java had final be the default and non-final be the thing you had to call for. It's as if you had a version of Java where static is the default and you have to say non-static everywhere in order to get the good code. That's kind of how final is. So what can you do? I don't know. We have some ideas, but we're not ready to. It's probably an intractable problem. In any case, immutability, even if you have to code extra for it, is important. Frozen arrays are something we need, I think. We need boxes that really work. We need immutable final methods that really are immutable and can't be remuted by clever serialization required set accessible true hacks. We probably need frozen objects, although that's debatable. An object that was originally mutable, make it frozen for shareability. There's some stuff with identity which I won't go into, but the key problem with identity is, here's coming to a towel near you, the strong box, the box which has too much of its own identity and semantics, and you need to track. Some people actually synchronize on strings and interned integers. It's just horrific. But so we basically need to say, okay, there's a new kind of box, which is the lightweight box that you can't synchronize on, that you're not going to be able to capture the identity of. I'm not going to talk about monotonicity because I'm out of time. But that's the sort of next step beyond immutability. It's the generalization. But one thing that I'd like to figure out in the next year or so is how to do lazy variables right in the JVM, so that it's something as a civilized version of what we do internally that's called stable variables. It's either uninitialized or it's initialized once, and the compiler can rely on that. I think that's a little piece that we need to add to the ecosystem. More vectors, but I'm going to leave that behind. Just a few things about Fibres. We want our threads to work for us. We don't want them to move in with us. When we're done with the thread doing whatever it does, it carries a computation fine. Oh yeah, it's going to carry a bunch of a whole AVX vector file and the other 10 kilobits of Intel per CPU state. Fine. But all I wanted to do was this one little thing and then move on to something else. I want to be able to have that fiber tail call some other fiber and not have to make a new thread to do the new thing. There's lots of things you can do with Fibres. Here are some possibilities, and a final bit. Yeah, there's nothing really new on this slide that you haven't seen before. A final bit is again the metacircular interpreter. The Bifrost is the name of the bridge, the Rainbow Bridge to Valhalla. And so exactly 1 year ago, after this very meeting, we were drinking beers, as I recall, and we realized that it was time to build a metacircular interpreter for bytecodes. And Brian got very excited, and he had a whole plane trip to think about it. And when he got home, he couldn't stop himself, and he went and coded it up, and it's actually there in the Valhalla repository, and it's really cool to play with. So I think one of the things we want to do with this interpreter is fiberize it. Take the frames that the interpreter builds and reify them and work with them with an API that decouples the computation from the current thread. It's sort of the BSM trick again. The interpreter is like a bootstrap method around your bytecodes to do something non-standard with them. Do you see a trend here? We're also going to use it to hack the meaning of the new bytecodes, probably. It's all hard, but it's fun. I want to say that there's a couple other projects, one in Oracle Labs called Truffle, and one, I don't know who hosts it, called PyPy, which is, again, one of these metacircular interpreters. I think it's a good idea, and it's time for OpenJDK to play in this space. And one last towel preview. There's the Bifrost bridge. It's even marked properly with an access bit. All right, so that's all I got for you. Are we ready for a break?